Okay, so this is the start of the second session of the day. We got 2 talks on design, build, and hopefully fly, and then 1 talk on a rear diffuser for an Audi vehicle. So first is one of our design, build, fly team. I'll let them go ahead and introduce themselves and take it away. 22-ish minutes of the talk and then Q&A. Okay, go ahead.
Well, thank you guys for coming. We're the 2 AIAA design, build, fly teams. I'm Ty.
I'm Carson.
Shamir.
Max. Joey.
Clayton. All right, so we'll start with the problem statement to kind of get you guys caught up to speed with what we're doing. So we have an electric-powered, remote-controlled airplane that must be designed, fabricated, and flown to follow urban air mobility missions that are provided by AIAA. And the missions consist of moving different configurations of payloads, such as the wooden dolls that represent crew, EMTs, patients, and passengers, along with a medical supply cabinet and a gurney for patient transportation. The airplane must be fabricated using viable manufacturing processes with an emphasis on a balance between payload weight, speed, and efficiency.
All right, so to start off with the rules and constraints, they're based off the 2023 AIA DVF rulebook. So just because there are so many, we're constrained on time, I'll just be focusing on the things that constrain us the most for this semester. So to start off with, the maximum wingspan has to be less than 5 feet. And also kind of unique to this year's competition as to the plane has to fit within a 2.5 foot wide parking space. So there's no length requirement in this, but unless we have a 2.5 foot wide wingspan, it needs to have some sort of mechanism to change the size to either folding or rotating the wing so that it fits. Then going to the propulsion side of things, the plane has to use an electric motor to take off within 20 feet of the starting line. And then going on to the 4 missions, so like Ty said, it's based on urban air mobility, and to simulate that, we're using wooden dowel passengers. So for the first mission, we have to incorporate a pilot and a co-pilot into the forward of the bulkhead. And then for mission 2, the medical transport flight, we have to use the same pilot and co-pilot, but also in addition, we have to fit in a hatch that's maximum of 6 inches wide on the side of the plane, a medical supply cabinet, gurney with a patient, and EMTs. And then for the 3rd mission, for the urban taxi flight, we have to use the same hatch, and we could have as many hatches as we want to fit as many people as we can possibly fit to simulate passengers. Then finally, for the ground mission, it's basically just to show that we can quickly switch between these configurations and show that everything is in working order. And then just to kind of show this, the people that I was talking about. So these are the sizes of the wooden dowel people. The gurney patient is slightly larger, but it'll be laying down on the gurney. And then this is our flight path that we have to go through. So from the starting line, we start with the right turn, then just to prove that we can turn both left and right, we have to complete a 360-degree turn, then finally complete the loop.
So here's our team layout. We voted on Ty Anderson to be our project manager. So this is just taking care of things like meeting notes, keeping everyone on track, developing our Gantt charts, which you'll see later on, and doing any interfacing with Dr. Fleming. From there, we separated ourselves into 3 sub-teams, kind of based on our own strengths and weaknesses. So the aero team consists of Ty and Shamir because they're in CFD. They were able to work on selecting the airfoil and developing our mission light calculations. Those calculations also tied into the electrical sub-team, which is Carson and Joey. They did quite a bit of work on developing those calculations and then also selecting the motor and propeller combination, looking into some research on servos and the batteries. And then finally, me and Clayton are the mechanical sub-team. So we looked into materials and manufacturing methods, as well as developing the CAD for the plane. Obviously, we did some background research because none of us are very familiar with the planes. So our first research article was winglet optimization. So this was just kind of a simple way to add lift to our plane while not increasing the drag very much. And then we also looked into the possibility of creating an S stand to evaluate the lift, which is this blue load cell back here, and then the drag, which is the red load cell. So this is just a way to actually test our motor and propeller once we get to that point, but these are kind of more second semester things. We also looked into some patents. So the one on the left kind of details a way that we could create a empennage that doesn't require tools to assemble. So this just kind of relies on dowels to kind of friction hold everything together. And then the other patent is a way to fold up our wings in a way that they're offset so they don't overlap, so we can get a tighter profile.
We decided to go with a high wing configuration for our RC plane, since it had great stability and it was simple to make. It was chosen or favored over the low wing, since the low wing scored relatively the same in most of the areas, but its stability was an area of concern. For the wing collapse folding design, we decided to go away from an actual folding design and instead routed for a pivoted wing, which allowed for a single spar construction, which would increase the wing's rigidity. And then for the empennage shape, we went with a conventional empennage shape, though we would have preferred a T-tail. The T-tail was a little less simpler to make, would require more intrinsically complex parts to construct. But its stability and control did show a little iffy areas of concern when tied into the high wing, which was chosen.
So now we can talk about our airfoil decisions that we went through. So the main things that we were looking at were the coefficient of lift versus the coefficient of drag, and that coefficient of lift versus the angle of attack, or alpha graph on the left. So the two NAC airfoils and the Clark Y are very similar. That one at the bottom there is actually the NACA 4412. That's
Move into the shot. There you go.
this one here at the bottom is the NACA 4412, which is the one we ended up going with. But on this graph, this is the Epler, and it has a very high camber, which is why it has a very high coefficient of lift, which kind of moves this up. But it does come with a very high drag, so that's why we ended up not choosing that one. Along with on this graph, you can see here the flow starts to separate once you get to a negative angle of attack, and since this is supposed to be transporting medical patients and whatnot, we wanted to make sure that in both the positive and negative angle of attacks, we have a flow that we can predict over the airfoils. So for that, we got rid of the Epler choice, and then we picked one of these three. And on this graph, the best one out of those would be the NACA 4412.
So we used decision matrices for some other components of the airplane. For the landing gear, we went with the tail dragger because of its better drag and design simplicity. The quad was also considered, but was not picked due to its drag, which was very high with the four wheels, and the landing stability was poor because when one wheel touches down, it might rotate the plane and flip it over. And the tricycle was a balance between the two, but the tail dragger won out. For propulsion configuration, we went with single tractor, mostly because of the cost and the efficiency and simplicity. Dual tractor was also considered, but due to the cost of having two motors and the complexity of it, we didn't go with it. Maximum thrust was good, but didn't outweigh that. Push was not picked due to the ground clearance of having a propeller in the back, and then push and pull had the negatives of having bad ground clearance with the propeller in the back and the complexity of having two motor systems. For the fuselage cross-section shape, the square and the rectangle were the highest. Square won out because of better support. Those scored higher because we're going to be using laser cut balsa, and that's easier to make square and rectangular cross sections with. Oval had good drag, but it's going to be much harder to create, and it doesn't constrain us that much.
Each team member was tasked with creating or recreating two plane designs, each totaling 12 overall possible choices for a final or semi-final plane design. Of those 12, we submitted them into their own separate design matrices that then refined us to these two planes. From these two planes, we decided to keep iterating plane number 2, since it showed better characteristics in its folding simplicity, since we would be now pivoting the wing. And its fuselage accessibility, while it's rather low, was still something that was considered, since if this were to be a scaled up plane, the passengers or crew or cargo could be stuffed under the wing rather than over and on top of the plane into the fuselage.
Our next steps after we had our refined design is we want to look at some materials to help us give us a better idea how we could further make this CAD. We looked at 6 common materials that we found in past created planes. Those 6 materials that were commonly came up were 3D printed material, carbon fiber, polystyrene, fiberglass, white plywood, and balsa wood. And after looking at the pros and cons of each of them, we decided that white plywood and balsa wood best fit our goals for this project. And they met our goals of a high strength to weight ratio, that good workability, easy to work with on campus here, and they also had an affordable cost. However, the other materials, we still want to consider them for other supplementation in our structure. Here's our current CAD design for our plane. The wing, the tail, and the nose and the landing gear are still a work in progress, but the main components of our fuselage consist of 1/8" laser cut copper light plywood, has ribs and kind of spars going along the length of the airplane. And we also want to include some balsa stringers kind of going on the corners for our fuselage to add extra shape and allow like a monocoat plastic film to attach over this after we can construct this. Looking a little bit closer at the structure here, where the main forces are going to be concentrated on our fuselage are where the wing has to rotate and where the landing gear is attached. For the rotating wing, we decided to include a wooden dowel to have the wing pivot on. In the fly configuration, the wing will reach a maximum wingspan of 5 feet. However, when we went in the part configuration, we plan on loosening some sort of fastener on that added rigidity next to the dowel, have it twist like a 2.5 foot wingspan. And also on our added stability here, we want to have anchor points for our landing gear so it doesn't shear off that landing.
So another kind of important constraint was that the passengers had to be restrained. So pretty early on, we came up with what we call the sandwich method, which is where the passengers are kind of friction fit into a 3D printed bottom layer. Then we take the top layer, which has kind of cutouts for the head, we put that on top. And then the current plan is to add either like kind of like a large bolt mechanism or a clamp mechanism to hold them all together and kind of complete that constraint of having them restrained. They're pretty easy to slide in and out of the doors. The pilots are a different case though, because they're able to go through a separate hatch because they have to be forward at the bulkhead. So the current plan is to have a clear piece of it because they see out of the plane, which would be easily removable kind of up there. And we would be able to just drop them into place and put the front cover back on and meet that constraint as well.
So kind of turning over now to our more design process and kind of where we started our calculations for this plane. The Aircraft Intuitive Design app for MATLAB, and it's a very popular tool used with teams for the AIAA design build fly competition. We had to make a couple assumptions in order to use this. So that's also why we did the airfoils earlier too, is because this takes that into consideration. But so we're starting with a weight of 10 pounds and a velocity of 50 miles an hour during cruise. We picked those because those are pretty similar to other winning teams with similarly sized planes from our competition. And these are also kind of like living numbers, and these will change as our CAD gets more defined. We'll be able to hone that weight in, and the velocity will change kind of along with that as well. So kind of to verify that this actually means something, we did a CFD analysis. So this is for the whole project, but the rectangular wing is what we'll look at first. And the drag that came out of CFD was 1.3 pounds at that 50 mile an hour cruise at 0 angle of attack. And it came out to be 2.6% difference between AID and CFD. And then we did for wing sweeps too, to do a little bit more research on those to see if it's something we might want to do for our project. We designed or defined the angle to be the chord length at the tip of the wing. So we did 2/3 of a foot and 3/4 of a foot, and that had a little bit of a reduction in drag, and again, had a pretty low percent difference between the two methods. And then kind of to verify that coefficient of lift at cruise that AID gave us, So they're reading about 0.5 for the coefficient of lift, and kind of looking at this graph that we talked about earlier. This orange one is that NACA 4412, and we have a 2-degree incident angle. So if you go up from there, it'll be about 0.5. So that's, we validated what we've gotten from AID. And now we can talk about kind of what we use AID for.
Okay, so here's some arrow calcs. We did a constraint analysis. So on the x-axis, we have wing loading, which is the weight of the loaded airplane and the square footage over the square footage of the plane wing. And then thrust loading, which is thrust in pounds over weight in pounds, loaded weight of the airplane. So we have some airspeed requirements on the left side, and then the takeoff requirement on the right. Since our wing loading is constrained, basically, or the S is constrained because we can only have so big of a wing. Any area above this design region is valid, but will be somewhere on this blue line because we're constrained by that. And then we also did some looking into dynamic thrust data. So since we're using a propeller driven airplane, as the airplane goes faster, the thrust decreases from static thrust. And that's a problem because our takeoff speed is not at 0 miles per hour. So we use this in our takeoff calculations to determine how much actual thrust we have at takeoff speed.
Since the plane would be doing 2 180-degree turns and a full 360-degree turn, it felt fit that we calculate the stall velocity for these turns. The stall velocity was calculated using the first equation, and then the radius of the actual turn was calculated using something called a loading factor, which is essentially just a ratio of the maximum thrust over the weight of the current plane, multiplied by the lift to drag ratio, which is also at its maximum. As it stands right now, with the current iterations of weight that we have right now, as the plane gets heavier, our turn velocity or our stall velocity has to go up as well. And our stall velocity also increases with every 5-degree pitch for the bank angle.
All right, so again, because our takeoff distance constraint is 20 feet, and it's much smaller compared to previous years, or sometimes double or even triple that amount. We figured it is a good idea to look at it early. So just based off this equation, weight is a big factor into the takeoff distance. So more weight equals a higher takeoff distance. And so I made this graph just based off this equation and Joey's dynamic thrust data to see the correlation between the requirement of static thrust that we would need based off the plane's weight. So just for example, we need a 14 pounds roughly of required static thrust for a 10-pound plane. And this would eventually go into our motor prop combo, like how we choose it basically. So just all these combos are just based off of what previous competition winners have used. And the manufacturer data that we found online and their recommended propellers. So just based off looking at these smart feed motors, these are more of the name brand motors to my understanding. So they cost a lot more, and just based off the price alone and our current budget, using almost a quarter of our budget on just the motor prop combo didn't seem very viable. Right now, our best option of these motors is the T motor AT4130, just based on the price not being too far off of the other motors and the maximum static thrust being the highest out of all of them. But the only drawbacks are the motor weighs a lot more than the rest, and the recommended prop diameter of 17 inches is higher than some of the other prop diameters. So this kind of draws issues for ground clearance. So when we take off, we don't want to be mowing the grasses.
So me and Clayton were part of Dr. Severe's FEA class. So we were required to analyze something that's a common failure point. And Dr. Fleming talked to us about how in past years, the landing gear has been a failure point. So we decided to create 2 different geometries. I created the vent bar geometry, which is a 1/4 inch thick piece of aluminum. It has some weight reduction in the form of filleted triangles. And
I created like a wireframe design that uses 1/8 inch cold finish steel wire. We both created several designs of these landing gears until they met our positive margin of safety for our estimated loading. And just want to note, with this analysis, we didn't look at the connection to the airplane as an area of concern. So that's something we could look at later, but both of these designs can be used for airplane depending on, like where we want to go proceed with.
Quickly, this is just a recap of what we talked about basically for the fall semester. So spent a week basically initializing our team and then started with preliminary research in our early stage design and then went into component research like the prop motor combos, along with kind of airfoil research. And then most recently, we've been doing, thank you, the refined design calculations and then those numerical analysis projects. So for the spring semester, we'll start off spending about 4 weeks finishing up that aircraft design and implementing some of the things that we've talked about today that aren't exactly finished yet. And then doing things like the doors and the control surfaces. And then after that, we'll spend the majority of the term manufacturing the plane. We plan on having a kind of test piece section of the wing that we're gonna practice built up monocode, make sure we're good at those things before we tackle the full plane. And then we have the first test flight date on March 29th. Then we'll have 2 weeks to iterate the design. Then on April 15th, we'll have test flight 2 with another little bit of time after that to kind of tune the plane. And at that point, hopefully our plane will be flying, but just in case, we have about an extra month before graduation for us to add a little bit of time wherever we need it. So that's our presentation. You guys have any questions?
Thank you. All right, so we'll open up the questions, first from the committee, which is me. Lucky me. First off, I thought it was rather funny, the idea of holding your passengers in place with friction. Very Spirit Airlines of you. So I thought that was kind of funny about like, all right, let's go take our airplane ride and just jam yourself in there. Just got a good laugh out of that. But I appreciated the design process. You really showed problem statement, objective constraints, backgrounds, multiple ideas. I thought that was really nice. Questions then. The NACA profile, 4412. It looks like you had a couple of thoughts on ways that you could go with that particular profile, but it was not clear to me that it was based, I mean, there's literally thousands that you can choose from, right?
Yeah.
So where did you even begin to think about including 4412 as something you're thinking about? Just to begin.
Initially, the first kind of one that we looked at was the Clark Y. And we saw a lot of teams were using that. So we kind of started there with that Airfoil Tools website and found similar airfoils to that. And then we kind of basically a lot of these and thinned out from there. Because also with MATLAB AID, most of the support for that is with the NACA airfoils. So we wanted to make sure that we could, everywhere we did our design, we could use that airfoil.
Yeah, what's nice about the NACA is the 4 numbers, you just put it in MATLAB and it knows the profile. It's like super helpful.
Yeah,
right?
so that was another big decision. I would think that one.
Okay, but I just need to know that it was based on some heritage of some kind. If you say other teams have used it,
Okay.
it's not the best answer, but at least it's an answer.
Yeah.
Okay. Another question is your ribs and spars. You've got some cutouts to reduce weight. Obviously, you went with kind of like square or rectangular, which is going to end up having higher stress concentrations at those corners. Can I just ask about how you chose the cutout shape, the triangles, the squares, just the general shape of this thing? Where's that coming from? Thoughts there?
Well, so your reason that it's rectangular here is because we want me to fit people in here, and in order to fit like kind of that
Friction fit in the middle there.
we chose a rectangular fuselage design because that's you could fit the most cargo in there and like the least area, so there's less wasted area.
Okay.
So that's kind of why we had to chose that here. And then we speaking in back for the triangle cutouts there, those are mostly just for weight reduction. We try to add the fillets in there to reduce the stress concentration in the corners there, but there isn't really necessarily exact like size reason from it. We just want to try to maximize weight.
Yeah, I understand that. It would be nice to see a little bit of variation, maybe circular cutouts, because maybe that's easier to manufacture or something. Just some comparison would be nice to see there, but okay.
We hope to get like the material on hand and like that soon in the spring semester, and like we're going to do some like more tests that we practice the laser cutter and see how it cracks.
Yeah.
And how it,
That laser cutter is pretty awesome, by the way. You'll be happy with that. But
Problem on that.
go
How
ahead.
much of that is going to be put, or actually of your force or your load through the structure is going to be on that
balsa sheet like on the bottom? Or do you have some additional support structures internal to help distribute any forces?
Yeah, that's what I have on the next slide there. We have, we want to go with this, a stronger, wood material, maybe balsa, but possibly some denser wood, that will actually take the most of the loading from the landing gear and the wing.
You get to grill them whenever you want, okay? Come on. No, I'm just kidding. What happened to your winglets? You found some research paper that said they're helpful and now you're not, now they're not on there.
That was more of a second semester type of
All right.
research thing.
Look into parasitic drag if you haven't heard about it. That's what they're for, more or less. Okay, last one for me is a lot of the design decision matrices that you had are nice. Don't get me wrong, but you have various missions that are part of your competition. And my question is, did you ever find that you have design decisions that you had to make that were varying depending on the mission that you're going to run? I didn't see that as any sort of decision point in anything that you did here. Can you just talk about that a little bit?
So I think the main thing. So the main thing we considered in the decision matrices was getting those friction fit people in there. But a lot of the missions, the things we have to focus, like I said, or what was said in the problem statement is we need efficiency, we need to put a lot of weight, and these kind of came down to that. And a lot of it came down to the 20-foot takeoff, because that's just a hard constraint that we have to hit. We're assuming once we get in the sky with the maximum payload, we'll be able to make those turns. But for the most part, it's just different weights.
Which of the missions is the most constraining to you?
Well, I think we're gonna do the hardest one is the one with the people. We have to put as many people in there. We haven't done calculations on which one's gonna be heavier, because another mission has a medical supply cabinet, which is based on just how heavy you can make that.
Yeah.
So all those boil down to, can we take off in 20 feet with the maximum weight?
Okay, cool.
Yeah.
Also, to add on top of that, just based off the rules, mission scoring, the mission 3 with the people, that's actually like the mission where you can score the most amount of points in, so it's probably the most important.
Okay. All right, maybe we got one from general audience if the other DBF team wants some grilling on. Or are you gonna be nice to each other and everyone's gonna hold hands?
Yeah, we gotta ask questions next.
Yeah, I know. So that's why you gotta watch it a little bit. All right, go ahead.
Your payloads in, what kind of door are you guys thinking of using for that? Cause right now it's just open.
Well, we're looking into, using some sort of magnetic detaching door for there, so something without hinges, just to reduce weight. It's tiny magnets on the inside, you could just put a piece of, balsa sheet over it.
And it's relatively easy and very simple to do that, since we do have 5 minutes where we can touch the plane before it actually has to do its ground mission or the flight mission. So it would be kind of the easiest way to just drill in or offset some like neodymium magnets in there that are impressively strong, and fit them into, you know, a cutout where the door would actually be. So that way we don't have to worry about parasitic drag for the hinges that are popping off if we're using hinges, or we don't have to worry about if the plane happens to, for some reason, lose both of its wings and fall onto the ground. If we had like, which it may not, if we used a mechanism similar to like the back of like toy batteries where they have like a little clip, if the structure of the plane changes at all, that clip is essentially now obsolete. So magnets and some sort of squishy material are kind of up for grabs right now. But we are still looking into some, you know, better alternatives than just magnets.
Okay, thanks, guys. We gotta change over. Next victims.
I would say the batteries are small.
All right, just give me 1 second to finish up here with. Give me a second.
Yeah, that's fine.
Okay, look at that. 11:15, right on the money. Okay, we're continuing the session with another design edition. Go ahead, take it away. 22-ish minutes and then Q&A.
All right, hi, everybody. Thank you for coming today. We are Team Icarus of the Design Build Fly competition. And today we'd like to share with you our achievements for semester 1. Before we get into that, though, I'd like to take a minute to introduce the team. We have our hierarchy, starting with our advisor, Dr. Mark Fleming, followed by the team lead, which is myself. And then we break down into our sub-teams here. The way we decided the leads and sub-leads for those teams was based on our experiences, our abilities, and also general interest in the subject matters. So to start, for structures and materials, we have Jensen as our lead, Ryan is our CAD manager, Bree is in charge of programming, Derek is on propulsion, Dylan is on electric and controls, and then myself am in charge of aerodynamics. You can say here actually. Each team has defined responsibilities. We thought this would be important so that there was no confusion on who had to do what tasks. And we wanted to define this really early so that everyone had a general sense throughout the year what we were going to be individually working on. So our CAD is going to be in charge of all of those files, the parts, assemblies, and drawings. And also they will update those as we make design changes. Our structural team will be determining the fuselage shape as well as running some different analysis to determine what materials are going to be the best. The aerodynamics team is in charge of some fluid analysis as well as CFD with the support of Brianna here, since she was the only one of us that took CFD this semester. Our programming team will be implementing the controls and making the code for the flight programs. The propulsion team will be doing our thrust calculations and trying to find the best propulsion components, as well as choosing our battery. And our electric and controls team designs our electronics layout, as well as they will automate our flight control and also work with the propulsion team to help guide that battery choice.
For a little background of what the 2023 Design Build Fly competition is going to be, it is mostly centered around an urban air mobility airplane that is capable of completing 3 air missions and 1 ground mission that can, and the air missions consist of being able to accommodate crew, passengers, EMTs, and patients in a number of configurations. There are many different project constraints for this particular airplane. So these are just a few of the ones that would give us the most problems. Maximum wingspan of 25 feet. It must fit in a 2.5 foot wide parking spot, and it must be a bulkhead in between the passenger compartment and the crew compartment. The battery pack cannot exceed 100 watt hours. No form of assisted takeoff is allowed, and the airplane must take off within 20 feet of the surface. So the first mission is a delivery flight where there's only a crew in the airplane, so there will be no passengers. The floor layout will look something like this. However, the passenger compartment will be empty. There'll be a 5-minute flight window that starts once the throttle is advanced on the airplane, and it must complete 3 laps around the flight course shown here within 5-minute flight time. Landing is not part of the mission, but this is the flight path that will be for each of the 3 air missions. The second mission is a medical transport flight where crew, EMT patients, and a medical supply cabinet will be able to be accommodated in the airplane. Similar to mission 1, there'll be a 5-minute flight window where you must complete 3 laps. But landing is not part of the mission. You actually have to land the plane for mission 2. And then the third and final air mission is a urban taxi flight. So the same floor layout as mission 1, but for this mission, as many passengers will be put into the passenger compartment as we can fit. And we will complete as many laps within the 5-minute flight window as possible. And we must complete the landing as well. So the ground mission is just timing how long it takes to switch between configurations. We will start with our airplane in flight configuration. So wings folded up, completely empty, no passengers, crew, anything like that. And then we will have stopwatch go, and we'll have to switch it from parking configuration to configuration 2, configuration 2 to configuration 3, and then back to parking configuration.
All right, so once we identified our mission objectives and constraints, we moved right to doing some initial
research where we looked at articles, patents, and some studies that we found. On this screen, which particularly pertaining to the parking constraint, we thought that that was something we should highlight early on. The bottom left here is a patent for a telescopic wing, basically expanding or shrinking to try and compact the wing down. This one might be a little bit of a complex design for what we're trying to do here for this project. So we also looked at these detachable wings in the top right corner. So that patent we realized might not be very helpful because you aren't allowed to separate or have pieces come off the plane while doing the mission. It might be helpful for maybe transport or something, but might be a little complex just for that. And then in the bottom right, we found the folding wings patent, which would be probably be beneficial to us, saying that we're likely gonna have to look at something that will compact our plane by folding. So on this slide, we have 2 additional studies, mostly pertaining to aerodynamic stuff. We have this winglet study, which we found from a previous year's report. We're going to look at this to see if winglets are something that we need to look into, or if we can go with a simpler design of just a cutoff wing. And on the right side, we have a tail design study, which basically just compares the lift and drag of different tail designs, which would be helpful for us determining our tail design. So once we did that, we moved into component research. We took to the internet and just started looking up a bunch of different types of components and different types of components. We organized it in this chart. Over here, we have different wing placements and wing designs. Top right, we have our propellers, and the bottom right, we have different landing gear types. Over here, we have our cutoff wings, and then over there is a bunch of different tail designs. The way that we set up this chart was with a pros column and a cons column. We could just kind of compare differences for what we're going to be looking at for our project. And we used this and developed this while creating our own conceptual designs.
Yeah, so as Dylan mentioned, now that we had the background on some different designs, for example, wings, fuselage, tail, etc., we thought it was time for us to take our own stab at coming up with some conceptual designs. We decided every person in our group was going to come up with 2 designs, with the choice of one of them being more unconventional if we so chose to do that. So for example, we start with the top left here. This design, actually, that yellow represents solar panels on the top, if we wanted to look into that. We also have our box wing design. We have a twin boom, a delta wing, and also a fuselage shape that Ryan titled the egg. And so now we had to streamline this down into final design that we were going to just continue working with for the rest of our time. And the way we were going to do that was with an overall decision matrix. And the way we built this decision matrix was by defining some criteria. So we have our wings, fuselage, landing gear / propulsion, and our tail. Each of these criteria has different definitions that get filled in with each design. And each of those definitions has a criticality ranking, which is defined in that top table there. It's on a scale of 1 to 9, 1 being the least critical and 9 being the most. Each of these designs then get filled in, and they get a rating, which is again defined on a scale of 1 to 9, 1 being the worst and 9 being the best. And that rating gets multiplied by our criticality to get an overall score. These scores get summed up vertically to get total scores for each criteria, as well as an overall score for each design. Now, if we zoom out, this is actually our full decision matrix for all of our designs. And we could go about using this decision matrix actually in 2 different ways. One is vertically and one is horizontally. And what I mean by that is we could take each of our columns and look at the total overall score and pick the design which had the highest one, which is shown in this table here. Or we could move across it horizontally and use it in a way which we call the Mr. Potato Head method, which generally means taking the highest overall score for each criteria and combining them into a completely new design. That's actually how we ended up using it. And so we took, for example, top wing score, fuselage, landing, propulsion, and top tail. And we combined them into a new design. And I think this was the best way we could have used our decision matrix because our top wing and fuselage were from design 9, which was the best overall score. However, our propulsion was from, and landing was from design 12. And our conventional tail design, which one was actually from designs 6, 7, 11, and 12. So if we had just gone with design 9, we would have missed out on those other components that we deemed the best.
Right, so when looking into our final design and the components that go into it, like Anna was saying, we sort of made like the Frankenstein plane of what components were good, what components were bad, and how can we implement those good components into our final design for our mission. So when looking at it, our mission is essentially to make a cargo plane, transport plane that can carry load essentially from point A to point B. So to do this, we decide on a high wing design with a tail dragger style landing gear, a conventional tail, a single prop and a polar configuration, and a square fuselage with a tapered tail. So with all these in mind, we figured that this would be the optimal design for our application and ultimately the best.
So, like they said, I was the only one in CFD, so they tasked me with this. But so for the airfoil, we decided to do a simulation on 3 different NACA airfoils shown above. So the 23015, 4412, and 23012, because they're all different shapes. Sorry. We wanted to figure out what shape is best for our aircraft based on the size, the weight, and the airspeed that it'd be coming at. And so, yeah, the simulated airspeed was about 65 feet per second, 20 meters per second. And this was based on a previous year's report at a 0-degree angle of attack. The 2 pictures below are both the NACA 44112 or 12 airfoils. The one on the right is from a validation source that was found and used for this, my CFD report, basically. And the one on the left here is the simulation that I did. It isn't complete because there are some discrepancies, as you can see along the wall, but it is almost there. Has not been completed just yet, but will be in the coming weeks. And so I have some supporting plots here, including a velocity pathline plot. The one on the previous slide was a velocity contour, and then 2 plots showing conversions for the lift and drag forces. Of course, in CFD, conversions does not specifically mean that there was an answer or it's correct. So again, that's still in progress. And so for some of our calculations, takeoff, we will be continuing in the coming weeks. It was a little bit more of the complicated side. So we'll start with some of the climb calculations. These calculations were taken from a textbook named on the next slide, but it's called the General Aviation textbook provided by Dr. Fleming. And some pre-allocated values were used based on previous reports. For example, the lift coefficient that was used for these calculations is 0.06, with density being that of air because we're flying here. And the reference SREF in these equations is referring to the reference area of the wing, which is based on our predicted 5-foot wingspan, which is our maximum. And according to Dr. Fleming, that's a small wingspan, so we're aiming for that. And an 8-inch chord. These were decided based on the idea that a higher aspect ratio is better for lower drag. And so the reference weight we did was also 4.5 pounds. That was also based on the previous year's report. That also includes the payload. And so as a disclaimer, you're not seeing tabulated numbers yet because they aren't finished. It's an iterative process, still in progress. But basically this blurb is the same information from the previous slide, except saying that there's an expected range for this weight being 5 to 10 pounds. That is also based on Dr. Fleming stating previous year's weight ranges. And this thrust equation is based on the previous slide's rate of climb equation. So just trust me, it's the same equation, just reworked to solve for us. So we currently are having some issues with the values for the required power. And due to the drag force calculations being a little wonky, so we deemed it to not be a reliable source at the moment to make any purchase decisions. But again, this is an iterative process, and we are continuing this.
So for the component selection, I began by looking at motors that have a higher KV value. I looked at a 1125, a 1500, and a 1970 KV motor. Out of these three choices, the 1970 KV motor would be best based on the operating conditions, the nominal power, and the maximum current that can go through the motor. These are just three motors that are chosen right now. I plan on in the second semester going back and looking at lower KV motors and see how those would perform relatively. As the propulsion battery, a 22.2 volt battery is expected to perform better than the 11.1 battery because the 11.1 volt battery is just not powerful enough to. And we can just have a more powerful battery. The 11.1 volt battery is well below the power limits compared to the 22.2 battery.
Right, so when selecting the material for this aircraft, really had to take into consideration three factors. And that was, well, how much material do we really need? The strength to weight ratio of each material, and how much is this going to cost us, right? A very important question. But so roughly estimating how much material or stock we need, we'll need approximately 40 foot of material for our aircraft. This is just for the fuselage alone. And like I said, it's a rough estimate. So as design changes are implemented, this number can or cannot change. But ultimately, so for our wings, we decided that the main materials are going to be balsa wood and monocoat. So we're going to be using balsa wood for our wing spars and ribs. It's mainly due to the fact that balsa wood, we can use it for a spar and sort of like a vertical orientation. So that way there's not as much bending or flex in the wing. One of the tests we do have to do as well is we have to hang a 20-pound weight from our aircraft while the wings are fixed at the ends and just see if it breaks, I guess. We'll see. But yeah, so balsa wood we chose because it's cost effective, lightweight, and in that orientation, we prove it, or we think that it can be strong enough to withstand that 20-pound weight. The monocoat will be used for the wing skin. We chose monocoat for this because it's a lightweight, cheap material. And although it is low strength, the wing skin isn't really like a high strength application that we need to consider a high strength material for. So monocoat would work perfectly for that. Now for the main body. So we decided to choose aluminum and balsa wood for our main body. Aluminum will be used for the main structure of the fuselage because we feel like it is an area of the aircraft where we will need the higher strength to be successful in our missions. Now, we do have talks, it's in the process, but we are considering maybe doing a mixture of aluminum or balsa wood and just putting aluminum in the higher strength areas of the aircraft. Which, I mean, this is a decision matrix for choosing the material for the fuselage. And like I said, that's assuming the fuselage is a continuous material, all the same. And then we'll be using balsa wood for the paneling of the aircraft. So the plan is the airframe and the structure of the fuselage is going to take most of the load and the stress. So balsa wood paneling would work perfectly because, you know, it's another low strength application, cheap, lightweight, exactly what we're looking for.
Okay, so moving into the CAD model, here we have fuselage, and at the time of creating this was about the time where we were looking into using aluminum tubing. So we kind of made it with a truss style structure here. And notice back here we have one cross member missing where we were figuring of putting the door. And we haven't looked into doing two cross members yet because we're still looking into the FEA. And as Jensen said, for the wings of the we were gonna fix it at or use a uniform distribution across the wing and then kind of use that in conjunction with this model to run the FEA. And you can notice there's a little bit of a tail drag here. And additionally, like Jensen said, because the wings would be fixed on the top here, we figured we might look into making the top part of the fuselage out of aluminum and then making the rest on balsa wood. For the landing gear, we chose to go with the trike slash tail drag style landing gear. We were kind of unsure what trike meant. So we were planning on doing 2 wheels in the front and the tail drag in the rear. And I made a simple model and some simple wheels showing what we were thinking of making the landing gear style like. But it was brought up internally that it might be a better idea to buy landing gear, so we wouldn't have to deal with the manufacturability, as well as making sure both of the wheels are symmetrical and going straight. So before we were doing that, we were going to go with the same kind of aluminum style, and the plan was to kind of have those have these kind of suspension arms cambered out to kind of take some of the load and act sort of like a primitive suspension. And so here we have the wing skin, and like the other group, we decided to go with the ribbon spar, which is usually what aircraft is going for. So we were going to do 2 stringers of balsa going down the entire length of the wing, probably most likely glued together, as well as some spars that we would cut out of balsa additionally. And as previously mentioned, we were going to use some monocoat to cover the wing. And as for attachment points, that's something we still have to go through with the FAA, like I previously mentioned. But for now, it would most likely be flipped on and then reinforced with a screw or something like that. And so moving into the interior of the plane, here we have the CAD model for kind of a modular plate system that we were going for. Using this piece down here, and notice how it extends out to both ends. The reason we did that is so that in case we needed to put a door on a different side, we could still put in these plates. So with having that piece fixed in the fuselage, these plates here have these little trapezoidal inserts to kind of slide it into place and then move it back or forward. And we had to break it up into 2 pieces because of one of the constraints being that the door could only be 6 inches wide, I believe it was. So we have it broken it up into 2 pieces.
About 1 minute, guys.
So moving into the passenger plates, it's the same style. It's broken up into 2 plates, and right now we just have it spaced into 8 on this bigger piece and 4 on the smaller piece. Just due to them not being allowed to touch each other. But in the future, we could look into kind of staggering these to fit more people in there.
Just to wrap it up, we decided we'd give you guys a visual representation of what we did for the semester. The top part is more of our weekly deliverables, which we are all able to complete on time. And that second section, more self-defined tasks, which are all still in the process and continuing into next semester.
Yeah, so these are our future plans for next semester. Again, we have it laid out in our milestone chart. We have our big goals here. And then coming right out the gate, next semester, we're looking to get that CAD finished up so we can start working on that FEA, CFD, finish those up. Then we're going to move into selecting and purchasing our parts. We still have some electrical stuff to look at, like servos, transmitters, receivers, stuff like that. And then we're going to look to construct it, test the plane out.
Cool, great, thank you guys. All right, we'll move into Q&A. Only got a couple minutes here, so let the grilling begin again. What is the max load for the vehicle? Last presentation, I think they said 55 pounds. Is that the number?
Yeah, one of the constraints was it has to fit within the AMA regulations, which has the max weight of 55 pounds.
Okay, so Brianna, it looks like a lot of the calculations you were using were based on 4.5 pounds. Is that right?
That's from previous MSOE report.
Okay,
Yeah,
so do you have an approximate weight for, I mean, that's a pretty big difference, 4.5 to 55. Do you have like a rough idea of what it's going to cost? Or like what it's going to weigh?
the weight, previous MSOE experience, I guess, was 5 to 10 pounds. So those are the numbers we're using. Whereas if you refer to previous, like higher competition reports, they're more like 30 pounds. But the max for the competition is 55.
Okay. So you don't really have an idea yet?
Our CAD is still like being finished up, and when that is complete, we'll have a much better understanding of, with our material selection and our choices for the design, what our weight specifically will be. But for our preliminary calculations, we just want to use a rough range to be able to get an idea.
By the way, I really like the name Mr. Potato Head for your plane, so I hope you go with that. Or Frankenstein's monster, that would also be quite good. Your Pew matrix was beautiful for your whole large whittling down the design. I love that, but I think you're missing some Pew matrices for the component selections. So what I mean by that is, like, Derek, you got your motors and your batteries that you got to consider, and you're like, oh, these are some that could work. But I think it would be nice to see a Pew matrix where it was like, this is what it weighs, this is how much power I get out of it, this is what it costs, like with a little bit more detail. Same with like batteries, right? And it was kind of the same idea with the landing gear. It was like, all right, landing gear, we could buy this, we could design this, you know. I think a little bit more care could be taken with like making a design decision for individual components, especially after you had such a beautiful Pew matrix for like full selection. Okay. That'll be it for me. I think we got to like make it quick because we kind of out of time here. Maybe one from the audience if we have one. Oh boy. Let's hear one from the other group. So Clayton, I guess, go ahead.
So you guys want to use aluminum rod for your fuselage? How are you guys planning on connecting those joints? Are you like TIG welding or is like this?
Yeah, it's just some sort of welding process. Yeah, I think that's what here my head will do.
Okay, maybe one more quick one, Shamir. Yeah.
What was the reason for the 0 degree incidence rate?
So that was just based on like taking one value from previous reports, because I didn't really have time to do all the angles for the simulation up to whatever we wanted. So in the table that was not shown in the calculations, it goes up to, yes, these are not good numbers, please don't look at them, but they go up to like 90 degrees for the angle of attack. Of course, it will not be or take off, I wish, but so yeah, so that's an iterative thing that's going on, but the 0 will just keep things consistent because we have values from previous reports to refer to that.
Okay, we got to call it here and move on to the next talk. So thank you guys. You said anyway. You want to? I don't know if you want to come on. Would be helpful. Give some feedback. I think that spot might be up. Hey. Wait just a second. We got 2 minutes, well, 1 minute still. So we'll wait until 11:45 in case anybody, wants to walk in the last second. And how are you doing? You said? You said?
I think so. Okay. Good, all of these, very importantly, this is the right.
Yeah, exactly. I don't know how you're naming your team 1 and 2. I really don't.
I think it's been 1 to 2.
Yeah. Okay, well, 11:45, I guess we'll go ahead. We'll continue our session now, moving away from DBF into a ground vehicle. We're going to hear about an Audi diffuser, just kind of coming from a customer request. So we've got a team of 3 here. Go ahead and take it away whenever you're ready. Shoot for about 22 minutes and then a couple minutes for Q&A. Go ahead.
So I'm Thomas. I'm Caleb. I'm Nathan. And this is our design process for the 2014 Audi S7 rear diffuser. So to start, we're going to kind of explain what a rear diffuser does for the car. Here's some examples of existing rear diffusers that exist for Audi vehicles. So the rear diffuser creates lift and drag for the vehicle, along with some cosmetic parts of the vehicle. Obviously, carbon fiber in general is created to help with cosmetic things, along with being lightweight and good for vehicles. So here's our design process. So first, we're going to start with our problem statement, our constraints and objectives, our background research. We're going to go through some Q matrices on our design concepts and our design making processes. And then we'll have a schedule on the manufacturing and testing. So here's our problem statement for our design. The rear diffuser of the 2014 Audi S7 does not achieve the same aerodynamic properties as the newer age models. The customer, John, would like a lightweight rear diffuser to sell as an aftermarket part to increase the aerodynamic properties of the vehicle so that it can compete with modern day S7 models. So here's some constraints from our customer. The project must meet our budgetary guidelines set by Dr. Hart and John. That's $1,500. Our diffuser must be a carbon fiber epoxy composite. And on the next slide, we'll be going into kind of, what is a composite and things like that. And then our material and design of the diffuser must be able to withstand Wisconsin winter temperatures of at least -50 degrees. We set that -50 as a guideline, as hopefully it never gets that far down there. Now we have our objectives of our project. These are set by ourselves. We'd like to manufacture a structurally sound and voidless composite diffuser. The less than 1% is an industry standard for composite manufacturing. We'd like to study and test the coefficient of drag and lift of the diffuser in the wind tunnel. That's downstairs in the SG01. And we'd like to manufacture a composite diffuser that is lighter than the current diffuser for the Audi S7. Right here, we have our current stock model of our diffuser for the S7. And we'd like to study and test the strength of the diffuser, trying to make it withstand a 10-mile-an-hour impact into an immovable object. Our example for this was a snowbank coming out of the garage, bumped into a snowbank, don't want it to break. So for subsystem assignments, I'm the project lead. I'll be handling all the PowerPoint making, scheduling, reporting, communicating with Dr. Hart and our customer as well. Along with that, I'll also be doing our manufacturing method.
I'll be doing our modeling, so making sure that the part is dimensionally accurate and fits onto the back of John's car, as well as the CFD. So just obtaining our coefficients of drag and lift, as well as figuring out how some of our design implementations impact our results.
I'll be doing, making sure that the car will properly mount to the appropriate mounting pieces on the car that are already here. That will line up also with the stock diffuser. I'll also be doing the FEA analysis, making sure that we can withstand the 10-mile-per-hour load put on the diffuser. So a little bit of background on composites. A composite material is a multi-phase material made up of 2 or more physically distinct components. We can manufacture this using glass, polymer, or carbon fibers. So a composite is made up of a matrix, usually epoxy, that is encapsulated, that encapsulates some sort of reinforcement like the glass, polymer, or carbon fibers, and it is combined with some sort of interface bonded together. Benefits of our composites include achieving more lightweight part, better mechanical properties, and some more flexibility. Major drawbacks of the composites is that they can be brittle. So when John might be backing out of the garage and hits the snowbank, there's a high chance of the composite breaking.
All right, so now some background information on composite manufacturing. So first off, we'll start with the Vartum technique. That is a vacuum-assisted resin transfer molding. Specifically for this demonstration, I'll be doing the dry manufacturing technique. Some negative pressure pulls the epoxy into the mold. So there's a resin inlet and the vacuum outlet is at the very back there. It pulls the resin through the part, purging air and filling all cavities with resin. Once that is done, it is left to cure. And so this is one of our considerations for designing our part. And this is done using an open mold, so just a 1-part mold. Next, we have our vacuum bag prepreg. So prepreg is defined as a carbon fiber fabric, so kind of similarly shown in the beginning. Just a 2x2 twill weave fabric. It's pre-infused, kind of shown here. It's dripped into a resin bath and then partially cured in an oven and sold as is. It's usually sold frozen. This prevents activation energy of the other curing agents. And this can be done using an open mold vacuum bag technique as well. The vacuum bag is set on top of the mold. The vacuum pump pulls the air out of the vacuum bag mold and prepreg system, purging all the air and compressing the fiber or the fiber fabric to the mold itself. And our last manufacturing technique that we researched was compression molding. Specifically, this is from a company called Easy Composites. They do a lot of different tutorials for prepreg, Vartum techniques, and compression molding. Compression molding uses heat and compression to form the part, kind of shown here. He presses it down and any excess resin is leaked out. This has to be done with a 2-part mold, so a top and a bottom. Obviously, it needs to be compressed. You can't just use a vacuum bag to squeeze the air out. This is done with short fibers, not woven fabric. So short fibers are kind of shown up here. They're a little more particulates of carbon versus like an actual fabric you can hold. So this was our last one that we considered for our methods. Now for mold manufacturing. Our first one we considered was 3D printing our mold, specifically with FDM, which is fused deposition modeling. This provides us high temperature applications for our cure cycle. So when we cure our epoxy, generally 300 degrees is our kind of guideline for how hot the material needs to be for our mold. This can be easily done using our on-campus resource through the Rapid Prototyping Center on campus. Our next one is the foam casting. So if we were to do this one, it would be hand carving. So we would set our diffuser on it, we would draw it out, we'd actually hand carve out, and we would make any design specifications that we'd want for our diffuser by hand. So this is a little bit of a dimensional accuracy issue. However, it is probably the easiest way for us to mold this, as we have a lot more hands-on ability on this to modify it and to do things like that. But like I said, the dimensional accuracy issue is definitely a problem with this manufacturing technique. For our last mold manufacturing technique that we researched, this is machining. Obviously, very expensive. Most high dimensional accuracy out of the 3D printing or the foam molding. Also sufficiently meets our curing cycle as it's either steel or aluminum. However, tooling is extremely expensive for machining. So this was one that was not as much considered as the other ones due to tooling costs and tooling time to create tools. I'm pretty familiar with manufacturing and tooling, stuff like that.
So I'm sure as most of you know, we have different elements that we can use to do the FEA analysis. There's also different software out there. There's just a few examples on the side over here, the Hex and TET. Obviously, there's a bunch of different softwares out there. A couple of different ones are ANSYS, which is one that's provided by the university, as well as Altair. We can get an educational license from Altair, but it's not as high tech as a professional license might be. So I researched a bunch of these and we'll dive into which one I decided to a little bit later.
A little bit of background on CFD. So computational fluid dynamics simulates flow motion using Navier-Stokes equations. And there's 3 main steps basically to performing this process. You have pre-processing, processing, and post-processing. Pre-processing is the most time consuming part. That would be basically just modeling the part in SolidWorks and then meshing it properly, applying boundary conditions, stuff like that. Processing would be actually running it and make sure it runs properly. And then post-processing would just be getting all your results. So for us, it would be getting our coefficients of lift and drag, figuring out how many fins we want to put on this part, how big our fins are, stuff like that. And it's important to know that it provides a good prediction for you, but it's not a substitute for physical testing. So we're going to be physically testing this part in the wind tunnel downstairs. And then this figure here is from a research article that we found. Basically what they did was they modeled up a sedan, like just an outline of what a typical sedan might look like. And they found various velocity and pressure distributions from it, changing the diffuser angle between 10 and 12 degrees on the part. And they found that the 12-degree diffuser angle yielded the best results. So they found a coefficient of drag of 0.28 and a drag force of about 120 newtons. Typically, for an accurate sedan, you'd want to be within 0.25 to 0.3. That's kind of like a typical industry range. And then we figured that we would test diffuser angles between 5 and 15 degrees just to get a larger range, because there's some diffusers out there that utilize a 7-degree angle. So we figured a larger range would just give us better result in the end. And then these are some initial diffuser designs ideas that we drew up at the beginning. You have a 3-fin idea here and then a 4-fin. These would be the fins right here. And the reason we elected to go with 3 and 4 is just simplicity. They're a lot easier to manufacture. But we figured that since a lot of cars
in practice use 5 fin designs as well. If the 3 and the 4 don't give us the results we want, we can always try going with a 5 fin design. But again, we prefer to stick to 3 or 4 if we can, just for simplicity purposes. All right, so now onto our subsystem selections. First off, our manufacturing method and material. I've chosen the carbon fiber prepreg from Easy Composites, which is the same company that did all those tutorials I was talking about earlier. First off, I'd like to kind of explain our Q matrix here. So we have our importance ratings based on cost, ease of production, accuracy, and time. And all items are design considerations. We're given a score between 1 and 4, 4 being the best, 1 being the worst. As you can see, the prepreg was given the highest score. I think it's the easiest way for us to properly manufacture a voidless, less than 1% composite material. It was also not as expensive as the Varden techniques, as there's not as many materials that go into manufacturing prepreg. We don't have to buy a fabric and an epoxy separately. Again, so one. My favorite mold material, I chose 3D printing, similarly ranked Q matrix as well. 3D printing gives us the best accuracy, similarly to machining, and it doesn't cost as much as machining as well. Easiest production is mostly hands-off approach. We can just send our model to the rapid prototyping center and the mold will be created for us. And so this is the least amount of time for us. So that way we can test our manufacturing methods and techniques along when we have our 3D printed mold printing.
So for the software that we're going to use, I decided to use ANSYS mainly because I'm in FEA class with Dr. Stoyanovich. And I know how to apply all of the boundary conditions and supports and loading onto the part. The biggest learning curve is going to be making sure that the composite and the curved surfaces of the part are properly modeled within ANSYS. We had a couple other options here. The biggest downfall to Altair and FiberSim was 1, cost, and B, being the learning curve that it took to actually apply loads and or making sure that the composite was properly modeled within the software. So for the element type, I decided to go with the TET 10 element just because it's going to be very accurate and it's going to be very easy to mesh inside of ANSYS, and it will properly model all the curved surfaces and complex geometry that we have on the diffuser. Some of the other elements were not as good with dealing with all the curved surfaces and complex geometry that we have.
For our CFD software selection, we decided to go with a combination of HyperWorks and ANSYS because HyperWorks is extremely good for curved surfaces. There's a lot of car companies out there right now that currently use it for their analysis. And they also are really good for meshing as well, better than ANSYS. So what we're thinking is we're going to use HyperWorks to mesh the part since it's better for meshing. And then we use ANSYS to actually get our results based off of that. And then for CFD element type selection, we decided to go with quad elements because they're very easy to mesh and they're pretty good for curved surfaces. Not as good as polyhedral, but polyhedral, there's a lot of computational time that's involved with using polyhedral elements. So we figured that quad would probably be a little bit better just to get results quicker. This is a manufacturing test piece that we made. It's 10 inches in length and 6 inches in width. We figured this would be something good to test our manufacturing methods on before we actually try to create the part, just so that we can perfect our methods and save some material in the long run. Yeah, this includes like surface prepping, folding and molding the actual prepreg to it, testing our cure cycles. We're going to test that here on campus in the curing ovens and in the materials lab. There's just a lot of things that go into carbon fiber manufacturing that we'd like to practice before actually trying it on our real mold. And we think this part too incorporates a lot of the things that'll be on our actual part, like the curved surfaces. So we think this would be a good piece to test some stuff on. Our initial plan is to have this printed by the Rapid Prototyping Center as well. So once we get that, we're going to do our surface prepping, our prepreg molding, and our curing cycle. We're going to do that after break, and I have that in the schedule.
So this is just a video of our current scan part from the rapid prototyping center. So, the reason we elected to get our parts scanned was to reduce the amount of error with our hand measurements, because it's a pretty complex part, and I don't think anyone really wants to hand dimension, like get the dimensions by hand of that thing. So we figured this would reduce a lot of the error. And then once we have this, we can use exterior softwares to convert it into something that we can actually render in SolidWorks, so that we can apply our design onto it, essentially. So I have an entire Gantt chart and schedule set up, and I decided for the sake of our presentation that I was just going to put our major deadlines in here. So we'd like to perform our CFD and FEA along with our testing, our mold, cure, and layup processes by middle to end of the week of January 16th and January 17th. This is the week after break. We will all be here during break, so we will be doing this after work from the 2nd until this day. We'd like to manufacture our mold by February 22nd. This relies heavily on the Rapid Prototyping Center's capabilities, but we estimate that this should be done by then. We'd like to manufacture our first prototype of this composite material by Tuesday, March 19th, and then our final product on Thursday, April 18th. So this gives us some buffer room before the end of the semester. It also gives us time to test the part too. Yes. And then I have a budgeting BOM in here. So the 3D molding is going to cost between $400 and $500. Our pre-preg is definitely our most expensive item. We're ordering this, like I said, from Easy Composites. That's $600. And then our backing bag tape and release agents as well. One more thing is that we're waiting for exact quotes from the Rapid Prototyping Center on the 3D scanning cost. The gentleman over there estimated for me that it would cost between $50 and $100. That's it.
All right, thank you. All right, we got about 10 minutes for questions, so start with committee members.
So you mentioned that you're gonna be using ANSYS and doing some simulations. What are you hoping to get out as your like performance metric from those simulations? And
Coefficient of lift and the best diffuser angle that'll give us the coefficient of lift that's like accurate, because basically the ideal coefficient of lift, it kind of depends on the shape of the car. So we don't know like precisely like what that number should be essentially, but we know that it should fall within that range. So I think the coefficients are the major thing we should be getting from our results.
okay, along those notes, you're gonna have to be simulating not only your part, but there's gonna be the entire car structure that goes into it. How much complexity you're gonna put into your simulation to try and get that upstream flow characteristics? Are you just gonna look at just the part? Or are you gonna try and?
I was gonna make something like that one research article had, where they made like the general shape of the sedan and then they just attached like the diffuser onto it. I thought that's kind of why I like that research article a lot, because I thought we could do something pretty similar to that. If that answers your question.
Yeah.
John, you can feel free to ask questions too. If you want.
I don't know. Yeah, we'll first turn on.
I was like, take a break.
Okay. So you're getting this epoxy, this pre-preg in. Where is it coming from? Do you know?
It's coming from the UK.
Okay. So you mentioned storage. Yes, you typically frozen. So if it's coming from the UK, how like, and then you get it here, how are you storing that to make sure it doesn't like expire?
Yeah, we have a freezer, industrial size freezer downstairs that as soon as it gets here, I'm gonna go get it and put it right in there. So make sure you're ready.
And then for your pre-preg, do you have a cure schedule?
Yes,
You do.
it starts, like I said, it goes to about 350. It's an 8-hour cure cycle.
At 350?
At 350, and then it drops to 180, and then it drops to 100, and then room temperature. There's a whole.
Over the course of 8 hours?
Yes.
Okay. And then one last thing, in terms of making your mold, did you ever consider machining foam instead of hand carboning?
No. That's definitely a good option. I still just feel that machining in general is going to cost us a lot of money. But no, I did not consider a foam casting, so that could be something we could definitely consider.
Kind of combine the two.
Yeah.
Do you have access to it?
Well, it depends on how big your wall is, but yeah, like potentially how powered the machine has been.
Okay, yeah, that would be super helpful.
Anything else from committee members or? Okay, general audience?
Yeah.
Actually,
So if I understood this correctly, you're trying to get a 2014 Audi S7 to perform on par with the current model year? Are you taking into account different suspensions, tire sizes, weights, the body itself to change drastically affecting aero? Will that be taken into consideration, or are we solely just looking at the rear diffuser?
We're definitely mostly solely looking at the rear diffuser as, obtaining SolidWorks and models of those kind of standard newer age Audi products like that is really hard to come by. We scoured the internet looking for even 2014 models of this or models of the actual vehicle itself. It's pretty hard to find that stuff. So in general, I would say we are constraining ourselves to mostly just the diffuser, but we're still looking on, we can make that kind of thing happen. So.
Thank you. And then, what do you guys mean by the, cause it's my understanding that a diffuser is actually kind of like the reverse of what an airplane is. It's actually like it glues you down to the ground. So it accelerates the air coming in, slows it down, and then equates it to the air coming out of the diffuser at the back end. So kind of like pressure recovery. It is what you guys are trying to say, is it essentially reverse lift?
Well, the diffuser creates lift and drag, right? I understand what you're saying. As the air comes in, it forces the car to the ground. It does create some type of lift at the end as well. So we like to optimize both that drag coefficient and that lift coefficient. Probably minimize the lift coefficient, maximize drag coefficient, because that is the purpose of the diffuser. As it sits on the car, it's supposed to create that downforce to stick the car to the road. So yes.
Perfect, thank you.
Anything else?
Is this car gonna be in like track conditions, so special? Or is it just like freeway driving?
Both. This is my daily driver, but I do try it. Kind of intent with your question. Could you analyze that one for your kind of CFD and all that stuff? And then take the new one and do that, and it kind of doesn't necessarily take the car out of the equation, but then you're comparing just the diffusers as an option.
Yeah, we could definitely do that as well. Yeah, our plan was to kind of analyze this thing first, and then once we render it to meet our design, see if our design improves it.
Kind of go up with Fleming's question, have you considered taking profile pictures of the vehicle itself and sort of building a CAD model as best you can off of that? In terms of,
Yeah, kind of the way that I was planning on modeling this thing to begin with was essentially just starting with a block and then just cutting from there. Because I mean, there's all kinds of different curves on it. So you're right to take a picture and get dimensions from that and just kind of trim away at it is kind of what I was thinking.
just to get a better idea of what the actual flow over the vehicle is.
It's a good idea.
So you mentioned that you're looking at some different fins. What effect do those fins actually have? Do you have any idea? Is there any sort of set?
It kind of just helps distribute the airflow underneath the car. So it's not very turbulent. It's kind of just very like
So there's been like a set configuration that might be more common, or is it?
That's another thing that also just kind of depends on the shape of the car. Like there's not like a universal number of fins or size of the fins themselves that yield the best results. It kind of just depends on the car.
So is that something that you said you were looking at like 3 and 4? Is that just?
Those are just typical, not like those. That's what most diffusers are that exist right now. So it's usually 3, 4, or 5. That's pretty much all I've seen.
And then I guess the last one I had is you said you were going to take it down to the wind tunnel to do some tests. Have you thought about how you're going to scale all of this down and how you set that up? Like scaling factors?
Yeah, personally. But
Yeah, we kind of were talking about doing the scaling before and with your test piece, testing that thing with the actual carbon fiber prepreg test that we have done. So we were going to test it with that. just to kind of see how the carbon fiber reacts in the wind, whether it flexes. We can take all kinds of measurements and stuff from that. That was the only way we had figured out on scaling it. We're having trouble with the molding and the kind of getting the CAD model set up and everything like that. So still early on things like that. Good.
Okay, and would you include like part of the car or like a tiny simulation of the whole car as part of that scaled model?
I think probably just the diffuser for the wind tunnel. But that's definitely something that we need to talk about as well. Is it's a good idea for sure.
Do you plan on like testing that out at FEA or like physically testing that?
Well, because of how expensive the pre-preg is, it's gonna be kind of hard to test it. The range of the pre-preg was what? It was like $600 for it, so it's gonna be not super cost effective to test it. It would be really, really nice to test it. Where I'm definitely thinking about taking one of the CFD models that we're gonna make, the smaller ones, and maybe scale test it, like Dr. Fleming was saying. Just scale testing it somehow, but it's probably gonna be mainly an FEA, making sure that we don't exceed our max tensile stress.
Yeah, because with $600, we don't have too many shots at making this part.
Yeah.
I mean, it's a very.
Well, you can make test coupons. You don't have to make a full part to
Yeah.
evaluate it, right? Like, I think she has a very valid point, and then I don't think you've defined your impact parameters very well. Impact is typically measured in something like joule. So if you have a 10-mile-an-hour car with some mass that you know, 1/2 mv squared, it's gonna give you your impact energy. It's kind of missing the mark there, and you could make a little plate and impact it with that amount of energy and see what happens, you know? So you have to make a full-scale part that costs $600 to evaluate that, right?
For that test that you're just talking about, would you try and incorporate that -50 Fahrenheit? Or how much is your material, like the strength of it differ at that temperature versus like an average day?
Obviously things get, shrink and they change as things get colder. That's definitely something that I've been thinking about. We haven't quite had an exact test made, but that definitely will be something that we'll take into account.
What happens to materials generally when they get colder? Not just they shrink, but also what?
It becomes more brittle.
More brittle. So valid concern.
So sort of follow up on your question. So you have a minimum temperature, do you have a maximum temperature you're gonna look at in terms of range or?
We have not set a maximum temperature. I think it would be good if we did set a maximum temperature. Obviously, it doesn't get stupid, crazy hot in Wisconsin like it might do in Texas or in Arizona. So I don't think we're too worried about that. But he's also testing it out on a track where there might be a little more extreme conditions that we might not have thought about yet.
All right, we gotta close the session here. Let's thank our speakers one more time. Good job. All right, so that's the end of the session. Thanks for joining us. We'll start up again at 1:15 in this room. All right, good job.
Thank you.
Good job, guys.